So welcome everyone. Our first speaker is Michelle Doering. She's a third-year PhD student in the Hasso-Plattner Institute, and she's currently working on social choice and temporal graphs.
Yeah, I know it's early in the morning, so it's quite good that I go through all the definition of temporal graphs in the beginning of the talk. But if you have any questions or anything is unclear, just ask. The title of this is not a title of the paper. There are two papers that I'll be talking about, but we will be generally talking about reachability in temporal graph settings and what that even is. Usually people have a motivating example. I do not. I motivate that we should read. Does it work? No, it does not. Is it off? Oh, I need to, yeah, sure. No, but it worked earlier, didn't it? Good point, that's working. Let's figure this out after. I want to motivate why we read preliminaries. And the first thing that we usually look for in a paper is the typical sentence. Okay, we have some graph, we call it a static graph, where we have some edges, we have some vertices. That's it. And since we read temporal graph papers, what we look for is that we have a tuple that also contains a time labeling. This is for me, this is the lambda. So every edge is not present every time. But this edge between A and B, the connection here is undirected, is only present at time step 1 and at time step 2. And the edge between B and C is only present at time step 4. Another way to depict this is that we may be given a sequence of static graph snapshots. So these two are the same graph. We can say at time step 1, we have the edge between A and B. At time step 2, we have the edge. At time step 3, there's nothing. And then at time step 4, we have the edge between B and C. And since when we talk about temporal graphs, we are usually talking about something moving through the graph, not only through space, but also through time, or we have some infection spreading, which we'll also see later. We also need the concept of temporal path, also called a journey. It has many other names, the same as temporal graphs. And for us, this is a sequence of temporal edges. So it's an edge, AB, and then a time step, make 1, such that the time labels are non-decreasing, because we cannot go back in time. And then the things that I usually look for when I read the preliminaries is whether the edges are directed or undirected. Usually people don't tell you. They just say it's a graph when it's undirected, and they tell you it's a directed graph when it's directed. But you can usually look at the pictures, and then you see either some arrows or you don't see arrows. The second thing that people also don't always tell you is whether they want to talk about strict or non-strict movement throughout the graph. Strict here meaning, we said before that the labels are non-decreasing. If the labels have to be strictly increasing, so taking a 3 and then a 5, then we are talking about a strict temporal path. And if I can instantly travel over an edge, so I arrive here, if I take the edge at time step 3, I arrive there at time step 3, and can then take another edge at time step 3, then it's a non-strict travel. And one can motivate this that a strict travel takes some travel time, so maybe something moving actually through space. And the non-strict travel is an instant communication. People talking at 3 o'clock can also continue giving the information away. 2 more restrictions that we can put. This labeling here, this function lambda giving some time labels to the edge AB. This can be restricted to simple. This means that if we restrict it to simple, then every edge can have at most 1 time label. Of course, the edge could also just not be present, like the one over here. And if we do not restrict our labeling to being simple, then that means that it might have 1, but it could also have more. Okay, so I do not mean non-simple when I say not simple. We can still have edges that only have 1 time label. And the last restriction is the one of restricting the labeling to proper. This name is not so good because it doesn't tell you what's actually going on. But what it basically wants to say that 2 adjacent edges do not share a time label. If that is the case, then we have a proper labeling. This can be achieved by just putting every label at most once, then this works. Or by just making sure here we have the time label 3 twice, that they are not adjacent. The one down here, the one that we have here, this one is not proper because we have those 2 edges that are both at time step 3. And this has some implications. One that we will see is that actually now there is no sequence of edges that are at the same time step. So basically, there's no difference between strict and non-strict. We will also see this later. And now, why am I talking about this? Because there are some papers that say in the beginning of the paper, yeah, we have some temporal graph, and now we make the simplifying assumption that we are simple and proper, like all the stuff about temporal spanners is saying this, and then they show something. Then there are other papers who have in the, I don't know, third page, a huge table where they have every combination. If you want to do the math, these are 16 combinations. They're actually only 12, but we will get to that later. And then they have a big table where either everything looks the same, everything is hard, everything is simple, very rare, but could also be the case, or there are differences. And the question that we want to ask is, does it actually make a difference what choice I make? And these 16 combinations, they were called temporal settings. It's tried to before. This is very small because I don't want you to read it. I'm telling you this is a paper and it's called Simple, Strict, Proper, and Happy, Study of Reachability in Temporal Graphs. It's by Casey, Cossini, and Sakar from 2024. And we're going to see some results of this because what they did is they defined this. If you make one choice, it's a temporal setting. So for example, directed, strict, simple, period. That's one setting. And now we want to know if it's different from saying directed, strict, and no, not restricted to simple. We want to know how much of a difference does it make to restrict myself in this whole situation. Any questions so far? Okay. And since in the title we had the word of reachability, this is actually what we're going to look at. Maybe one disclaimer, I am going to call a graph directed and strict, even though it's a bit weird, because directed is really part of the definition. Do I have directed edges or do I have undirected edges? But this strict travel through the graph is not really inherent. You cannot see it. I give you a graph and you cannot tell whether I want it to be strict or non-strict. But I'm still going to abuse notation a little bit and I'm going to call a graph directed and strict if I want it to be strict. Okay? Okay, let's look at a few examples. Very simple. Everything is very small since it's early in the morning. This is a graph. It's obviously not simple. It is not proper. And it's undirected. That's the only thing we know. And then we can look at something that's called the reachability graph. The reachability graph tells me who can reach who. It's like the transitive closure of a static graph. And this is what it looks like for non-strict and some notation for the rest of the talk. The black edges are always going to be edges that are also present in the footprint, just so that you don't have to check which of those are present in the footprint. Oh yeah, this is something I didn't say. The underlying static graph, without the labels, I call the footprint. And the orange edges are additional reachabilities that are given to me by powers of length at least 2. Okay? And if I have the non-strict travel, then I can take the 3 and the 3 and the 4. So A can actually get to D. And as you can see, here's an empty arrow. This just tells you that on the other side of the edge, there's no arrow, just so that you can locally see the out and in reachabilities. Because D can only take the 4 and then the 5, and then it's stuck and cannot get to A. So D cannot get A. And the strict reachability is much more limited because this 3, 3 that we have on the left cannot be done in a strict travel. So actually, A can reach C, but C cannot reach A. And as we can see, the reachabilities of this specific graph under strict and non-strict reachability on the strict and non-strict travel is different. That's an observation. Now, if we look at a proper graph, we observe something that we already said before. If we have no two edges that are adjacent, that have the same time label, then there is no travel that is only possible in the non-strict way. Every temporal path that I can choose has to take two edges that are actually strictly increasing. So the reachability under non-strict and under strict is always the same. And one last example, because there were quite a little labels on this. Quite a little labels on this here. We have a lot of, and here we can see this is actually that we have the same reachability. This is just an example that we will need in a minute. Okay, now what we would like to do is we would like to define a notion so that we can formalize what we observed here. We observed that if we have the setting of proper and strict in undirected or directed, and proper and non-strict, then it is the same. But we are mathematicians, so I studied math in my bachelor, so I say that I'm a mathematician. We need some notion, some equivalence relation. And we want to say that two temporal graphs are reachability equivalent if they have the same reachability graph. So this graph, non-strict, is not this one. The proper graph here, non-strict, is reachability equivalent to the graph that is strict. And actually here now you can see why I put a different graph. This graph here, the third one, is also under strict and non-strict, reachability equivalent to the second graph. They are not the same. We have even different names here. We have many more labels, but they are reachability equivalent because they can express the same reachabilities. And I said here isomorphic for the ones that do not know this notion. It basically means that we have the same graph under renaming of the vertices. This is how you can imagine it. You can just think of it, it's the same graph. Okay? We might have to rename the vertices. Okay. Now that we have this notion, we can compare temporal graph settings. Remember, a setting was undirected, non-strict, simple, proper. And we can say that one setting can simulate another setting. So, for example, proper and non-strict can simulate proper and strict if for every graph in the one setting, in the T setting, there exists a reachability equivalent graph in the other setting. So, for example, in the static setting, we know this. If I give you an undirected graph, I can make it directed by just turning it into two bidirected edges. So basically, directed can simulate undirected in this sense, because who can we choose still the same. Okay? And now we can even say that if a setting can simulate another setting, and even has another graph that cannot be simulated in the other way around. So, for example, I have a blackboard, as Nico noticed earlier. If I take this undirected edge, I'm talking static for now, because we will see some examples in a minute. Then I can turn this into this directed graph. But the directed graph that just contains this edge cannot be simulated by an undirected one. Meaning, in this reachability equivalent notion, directed graphs are strictly more expressive than undirected graphs. And this is kind of the same idea that Castell, Cossini, and Zakar introduced for the temporal graphs. We want to say if every graph, I have nice illustrations. If every graph in the one setting can be simulated by the other, but there exists one that cannot be simulated in the other way around, as we have it here, then S is strictly more expressive. Then, of course, the two settings can be completely equivalent if I can translate in one direction and in the other direction. And lastly, they can also be incomparable if there always exists one that I cannot translate. And this is just the formal notion that we are going to use. And now we could actually prove that any setting that's directed or undirected that contains a proper labeling and non-strict is the same as the proper labeling and strict. And this is why we actually have only 12 combinations and not 16, because the proper is just the same from the get-go. And now what we are going to see, what are we going to see? Yeah, we are now going to see some examples before I show you a nice hierarchy of all the 12 settings that we saw. And we are going to start most of those examples are very simple. This is also the feedback that I got from the reviewers. The examples are way too simple, but they show a very nice difference between two settings. And we are going to look first at some undirected settings. So what we are going to look at, if we have an undirected graph with a strict reachability, is it actually that it is more expressive than if I have undirected, strict, and simple? Basically expressing that if you have more labels, you can do more, which kind of makes sense. And how we are going to prove that is I'm going to give you an example, this one actually, that is multi-labeled. I put it here on purpose so that we recall that we don't have the restriction to simple. And I say this has reachabilities, those actually, that cannot be expressed if I can only put one label per edge. This is basically all we are going to do. And how this works is that we know, if I look at this reachability graph and I basically want to build this, I have undirected edges and I can only put one label per edge, then I cannot put an edge from A to C in my new footprint, because this would immediately create a reachability from C back to A. So the only edges that I'm allowed to put in my footprint are those, the ones that I had over here, the bidirected ones in the reachability graph. And now I can observe that I want A to reach C. So I need to have a path from A to C. And I can only put one label. I'm just going to put some numbers because it's nicer than having variables. But if you want the mathy one, then look at the bullet points. And we observe the same from B to D. B needs to reach D. But since we only have one label per edge to be put, this has to be larger than the two that I put in the middle. And I guess now you can see A can reach D, which is something that we didn't want to do. So actually what happened here, that we had the two labels in the middle, was kind of what we needed to allow this non-transitivity happening, right? This is one that we have a lot in temporal graphs. Reachability is not transitive. A reaches C, C reaches D, but A does not reach D, at least in the multi-label strict setting. Example number one, and now we have another very, very small example for directed. Oh, by the way, this is Castell, Cossini, and ICALP. They did everything for undirected and left one open question. I solved the open question, did it for directed, and then compared the two. And the second that I wanted to show, we just saw multi-label and simple, and now we want to compare strict and non-strict in the directed setting. And basically what I want to say is that this triangle, or rather any cycle, is very special when we compare strict and non-strict, because the reachability is just the thing on the right. Right? Since we are in the strict setting, we can only reach A and cannot continue on, which is kind of a bit of a cheat because I just put time everyone everywhere, but that's fine for us. And now if we basically do the same from before. Our footprint can only contain these edges, because if I were to put an edge from B to C, that would be kind of problematic. And now we kind of go the other way around. A must not reach B, right? In my reachability graph, A cannot reach B, which means that the edge from A to C has to be larger than the edge from C to B, because otherwise I can travel here. Even if it was the same, I could travel. If they were both twos, I could travel. And we have the same for C to A. C must not reach A, so whatever label I put on this edge must be larger than the label that I put from B to A. And I could put more labels, but more labels only give me more reachability. So actually, this is why we are still sticking to the simple setting. But as you can see now, we already have one transitive reachability along the cycle, along this triangle, which makes B reach C. Meaning that, and this is actually something that we try to formulate, that if we have a cycle in the footprint, and we have a non-strict setting, then we always have at least one transitive reachability. We cannot have just the cycle happening. Okay, two small examples. Here's the hierarchy. What you see here is just the title of the paper. This is the directed part, the upper one, because it would get quite cluttered if I also directed and undirected. And this basically says these are all the graphs that are directed, proper, and simple. I ignored strict and non-strict because they are the same if you put proper. Here we have two settings on top of one another. This is directed strict, it's directed strict and simple. And every arrow here and every non-existing arrow is one proof. So if we have this edge going from strict, undirected strict to directed strict and simple, this means that it can be simulated by it. So for every undirected strict graph, there exists a reachability equivalent graph that is directed, strict, and simple. Okay? And as you can see, here are open questions. If you want to talk about it, I heard we have some time after lunch. We can talk about that. And we saw, so this first before we talk about what we already saw, these green edges are just definitions. There was nothing to be done here, right? If I am restricting myself to simple, then of course I can simulate myself if I don't restrict myself to simple by just taking the same graph. So this was not really much of an effort. These two things we saw that if you have a directed strict graph, then it cannot be simulated as a non-strict graph. And also this one here we saw, strict to strict and simple. And yeah, they are very simple, but I can tell you they are complicated ones. They're going to disappear in a second, but I just want to tell you this is the crab. This is because it looks like a crab because it has arms and a head. And this is the open question that was left. And this is the alien. This is what I call it. And this was the most complicated one that I found. It was fun looking for it, but the other ones are quite small. Now, this is a bit surprising because what does it mean over here? This means these two are equivalent. I didn't tell you yet. Strict and directed strict and simple are equivalent, which is kind of surprising that we can do exactly the same if you only have one label per edge. But it's unfortunately also a bit boring. You can just, I mean, you saw it here. If you want a reachability, a temporal graph that has a specific reachability graph, you just take the reachability graph and put time label 1 everywhere. This gives you exactly the reachabilities that you want to have in the directed graph, as we have here, right? Because in the strict setting, we cannot travel further, which is a bit boring. And this is what I want to show you now. How many minutes do I have? 7. Yeah, we can do that. Because this is quite a nice transformation. What does it mean? Recall, every proper graph has a reachability equivalent graph in the non-strict setting by taking the same, right? This was just containment definition, nothing else. But actually, we can take any non-strict graph having many adjacent edges on time step 2, for example, and turn it into a proper graph while having exactly the same reachabilities. And we're going to see an example. The goal is we want to replace the edges at the same time level. So we have a lot of edges with time label 2, and we want to replace them all by distinct time labels to keep the same reachabilities, keep the same trips. I don't care where we go. We just need to have the same reachabilities. Yeah, so I could go directly from this one to this. So we're going to forget that they're time label 2. They all just have the same time labels. And we observe something on the right on the reachability of this snapshot. Kind of forms, we can look at this as a static graph with just directed edges, which means we kind of have a DAG situation going on. We have some movement with the graph. If we have a triangle, they are a strongly connected component because they can always reach one another. And if we don't have not a cycle, so no, then we have a weakly connected component, right? So each snapshot has up to n weakly connected components. If there's no edge, there are n, and if everyone kind of has an edge, then there's just one. And these things form the strongly connected component, and we can imagine this as a DAG. So we can move through here. If you know minors, we can merge them together into one vertex, and then we can basically move through the thing, and we have kind of an ordering over the vertices. And again, we just need to keep this reachability. And we can just replace the labeling here to follow this ordering. So first we replace the orange edges here, the DAG edges, in some order. 2, then something happens there, then 3, and here 4, and here 5. We could, of course, give this a 4 and this a 4, but I wanted it to be proper, and so this is nice for something else later, which we are not going to see today. And now we have to also replace the edges within each strongly connected component and just push the rest away. So what we are basically going to do is we are taking this time and spreading it out into seconds. So we need to be able to let those guys move to one another, and we can do this by just taking a spanning tree. You cannot really see it here because it's just a triangle, but even if it's larger, we just need to ensure that everyone can reach everyone else. And we can do this by just creating any spanning tree and then putting something that's called a pivot labeling. Has been used quite a lot, like in 1950, but 72, gossip theory, a lot more in recent years. What I basically do is I take one at the top, and I need my both hands, so should not fall. I have the root, I have my leaves, and I first go up in time, and then I go down in time. That's all. Yeah, that's the pivot labeling. And that's it. Then we just need to shift the rest. So the biggest time label before was 2, and now the biggest time label is 9, so we just shift the rest. And we just turned a graph in a non-strict setting into a proper graph with the same reachabilities. Yay! How much? 3. Okay. I have a disciplinary, and I was looking for a Venn diagram that can show this. Because what we saw is we have some reachability equivalents. They are kind of the same, doesn't matter. And then we have this funny hierarchy, and it looks a bit complicated. But we can see, okay, every undirected graph, we can turn like this into a directed graph, the same setting and stuff. And that's a nice triangle that actually shows the same, but it just looks a little bit complicated. Undirected forward symbol is the least expressive setting. If we can find an algorithm, a hardness reduction for this, then it follows for the rest. This is also usually what's done. We take happy is what they also call the simple and proper ones. So proper and simple undirected, and then you can follow the rest. So this is the most restricted setting, and it can be simulated by undirected, strict, and simple. And this is what one triangle being contained in another triangle means. It can be simulated as. And as you can see, non-strict and simple, and strict and simple, they are incomparable, right? They don't have a path to one another. And this is this triangle, undirected, strict, and simple, and this is undirected, non-strict, and simple. They are not contained in one another, so they are incomparable. And we can see something nice. This is why I like this. All the undirected settings are extended by all the directed settings. That's cool. This is the open question. All the non-strict settings are extended by all the strict settings, which is also something that we would expect. And it kind of looks weird for the multi and simple. I was hoping to also get kind of a triangle and another triangle, but kind of right now it doesn't look like it. And basically the open question is whether this triangle is here or here. And I don't know. And yeah, I guess that's it. Any questions? Yeah.
So the temporal path all include that you're allowed to wait at the vertex.
Yes.
But so there's nothing with waiting time restrictions so far.
So far,
in
yes.
settings. Yes.
Yeah.
I mean, some of them you can kind of anytime you can wait, you can just add a long path or something like that.
Yeah.
But in the other way around, it's probably
so
need to show that you can't.
Yeah, we didn't look at this yet. Yeah. I think the context numbers should still all work.
Yeah.
Most of it, I mean, the small ones should still work, and the big alien is also quite tight. Like the labeling is tight, so they don't weigh much.
Mm-hmm.
Michelle, can I ask a question?
Yes.
So thanks for the nice talk. First of all, I wanted to just quickly ask you, do you know anything about like the time complexity if you want to go from, if something is included in the other, how you can transform maybe? In some cases it will be trivial, but in some others.
That was done by Niels and others recently. This is NP-hard. So the strict and simple, whether you can realize one thing, or whether you can transform, you mean, or whether you can realize one thing. I think it's the same. Doesn't forget my question. Yeah, they showed that for strict and simple it's trivial, as you said, but otherwise it's
good.
hard.
Thanks.